Chip War. This video is based on key insights from the book Chip War by Chris Miller. Introduction. In August 2020, as the USS Mustin sailed through the Taiwan Strait, a quiet but incredibly important battle was beginning, a battle over tiny chips called semiconductors. Chris Miller opens his account by illustrating this tension, noting the ship's weaponry symbolized a traditional form of power, while the real struggle was shifting to the world of microelectronics. The U.S. Navy was demonstrating its presence, but the U.S. government was simultaneously focused on a rule change regarding technology sales, specifically targeting the Chinese tech giant Huawei. This wasn't about missiles anymore. It was about controlling the flow of computer chips. For years, the U.S. had restricted sales of military technology to China. However, this new rule aimed to limit Huawei's access to advanced computer chips, even those used in everyday products like smartphones. Miller explains that Huawei was becoming a major player, offering competitive prices thanks to support from the Chinese government. The U.S. feared Huawei's dominance in things like 5G networks would give China too much power and potentially undermine American tech leadership. Essentially, the U.S. was trying to prevent China from becoming the world's tech superpower. The importance of these chips is hard to overstate. Miller points out that China imports more chips than oil, highlighting their critical role in the modern economy. These aren't just for phones and computers, they're in everything from refrigerators to cars. China is worried about a chip choke, meaning a disruption in the supply of these essential components. This fear is driving massive investment in developing China's own semiconductor industry. If China succeeds, it could dramatically change the global economy and military balance. Miller emphasizes that the rivalry between the U.S. and China isn't about traditional weapons anymore, but about computing power. Modern technology, artificial intelligence, missile systems, even self-driving cars, all rely on cutting-edge chips. A small number of companies control the production of these chips, making them incredibly valuable and strategically important. The author explains that while we don't often think about chips, they've built the modern world and shaped how countries interact. Globalization itself depends on the trade of semiconductors. To understand how these chips work, Miller breaks down the basics. He explains that computers use ones and zeros to process information, and chips are filled with tiny switches called transistors that control these digits. These transistors are incredibly small, and modern chips contain billions of them. The author uses the example of the iPhone 12, which requires over a dozen different chips to function, and highlights that Apple designs these chips but doesn't actually make them. This leads Miller to the central figure in the story, Taiwan's Semiconductor Manufacturing Company, or TSMC. He describes TSMC's Fab 18 as the most expensive factory in human history, capable of creating chips with incredibly precise detail. In fact, TSMC is the only company that can currently produce Apple's most advanced processors. The author illustrates the scale of production by noting that TSMC fabricated over a quintillion transistors for the iPhone 12 alone. Miller then traces the history of the chip industry back to the 1960s, explaining Moore's law, the observation that the number of transistors on a chip doubles roughly every year. This exponential growth has driven incredible innovation and made computing power cheaper and more accessible. He notes that the success of Silicon Valley wasn't just about brilliant scientists, but also about manufacturing expertise, business vision, and a culture of opportunity. The author points out that while the chip supply chain is global, Silicon Valley remains at the center. America's scientific expertise, venture capital, and large consumer market have all contributed to its dominance. Other countries have tried to compete, but they've often relied on partnerships with Silicon Valley. Miller stresses that the current system is incredibly efficient, but also incredibly vulnerable. The disruptions caused by the COVID-19 pandemic exposed this vulnerability. Factory closures, supply chain issues, and increased demand led to chip shortages that impacted industries worldwide, including the auto industry. Miller explains that political leaders were caught off guard, realizing how much they depended on a complex and fragile supply chain. He uses the example of a typical chip, which might be designed in the UK, manufactured in Taiwan using materials from Japan, and assembled in Southeast Asia. The author emphasizes that a disruption at any point in this process could have serious consequences. He compares the concentration of chip manufacturing in East Asia to OPEC's control over oil production, noting that Taiwan alone provides 37% of the world's new computing power. He also highlights the importance of ASML, a Dutch company that makes the machines needed to create the most advanced chips. Miller warns that a natural disaster, like an earthquake in Taiwan or Japan, or a political conflict, could severely disrupt the global chip supply. Finally, Miller introduces Morris Chang, the founder of TSMC, as a symbol of the complex relationship between the US, China, and Taiwan. Chang's life story, born in China, educated in the US, and instrumental in building Taiwan's chip industry, illustrates the interconnectedness of these regions. The author concludes by arguing that semiconductors have shaped the modern world, and that understanding their history is crucial to understanding the current geopolitical landscape. He suggests that the battle for control of this technology will define the future. Part 1: Cold War Chips. Chris Miller begins his story during World War II, a time when winning wasn't just about brave soldiers, but about who could make the most stuff. The war was a typhoon of steel, as the Japanese called it, and it deeply impacted the lives of three future giants of the semiconductor industry: Akio Morita of Japan, Morris Chang of China, and Andy Grove of Hungary. Each experienced the war's devastation firsthand, witnessing bombings, displacement, and immense suffering. These experiences, though vastly different, set the stage for their later drive to innovate and rebuild. The United States emerged from the war as an industrial powerhouse. It wasn't just about building more tanks and planes. It was about building everything needed for war: copper, iron, rubber, oil, and aluminum. The U.S. understood that winning a modern war meant having a stronger factory base than your enemy. This focus on industrial production laid the groundwork for future technological advancements. While the war initially focused on traditional materials like steel, it also sparked research into new technologies like rockets and radar, hinting at a future beyond simple manufacturing. Morita, for example, worked on heat-seeking missiles, recognizing the potential for machines to think and guide themselves, a concept that would later become central to the development of computers. Early computing wasn't about sleek laptops or smartphones. It was about people, human computers doing calculations by hand or with simple mechanical calculators. During the Great Depression, the U.S. government even employed hundreds of people just to create tables of numbers. This showed the need for faster, more accurate calculation, but it was slow and prone to error. The war accelerated the demand for better computing, leading to the development of machines like ENIAC, which used vacuum tubes to perform calculations. However, ENIAC was enormous, unreliable, and consumed a lot of power. Vacuum tubes frequently burned out, and the machine was constantly plagued by insects, hence the need for debugging. It was clear that a better switch was needed to make computers truly practical. William Shockley believed the answer lay in semiconductors, materials that could sometimes conduct electricity and sometimes not. He theorized that silicon could be used to create a solid-state valve, a switch that could control the flow of electricity. However, his early experiments failed. It was his colleagues, Walter Brattain and John Bardeen, who finally succeeded in creating a working transistor in 1947. This device, though simple, proved Shockley's theories and opened the door to a revolution in electronics. AT&T, which owned Bell Labs where the transistor was invented, saw its initial use in improving telephone signals, but the potential was much greater. Shockley, driven by ambition, left Bell Labs to start his own company, Shockley Semiconductor. However, his difficult personality led 8 of his best engineers, to leave and form Fairchild Semiconductor. This group, including Robert Noyce and Gordon Moore, focused on making transistors more reliable and easier to manufacture. They developed a process called the planar method, which protected the transistors from impurities and allowed them to be built directly into silicon. Simultaneously, Jack Kilby at Texas Instruments was working on a similar idea, putting multiple components on a single piece of semiconductor material. Both Kilby and Noyce independently invented the integrated circuit, or chip. Kilby's version used wires to connect the components, while Noyce's used the planar method to create connections directly on the chip. Noyce's approach proved more scalable and reliable, laying the foundation for the modern semiconductor industry. The author emphasizes that while the invention was brilliant, it was initially expensive. The challenge now was to find a market for these new chips and to drive down the cost of production. This sets the stage for the future competition between the US and China, as both nations recognize the strategic importance of controlling this crucial technology. The launch of Sputnik in 1957 was a wake-up call for the United States. The Soviet Union's satellite orbiting Earth showed America wasn't as far ahead in science and technology as it thought. This sparked a huge effort to catch up, especially in rocketry and missiles. Chris Miller explains that this sudden need for better technology created a market for a new invention, the integrated circuit, or microchip. Bob Noyce and Gordon Moore, who founded Fairchild Semiconductor, quickly found themselves with a valuable product. The US government, worried about falling behind the Soviets, was willing to pay a lot for anything that could help. The first big customer for Fairchild's chips was NASA, the space agency. NASA needed computers for the Apollo program, the mission to send a man to the moon. These computers had to be small, light, and use very little power. Traditional computers using vacuum tubes were too big and used too much energy. Integrated circuits, which packed many tiny electronic parts onto a single piece of silicon, were the answer. Miller details how engineers at MIT initially thought building a lunar guidance computer would require a refrigerator-sized machine. Noyce's chips made it possible to shrink that down to something much smaller and more efficient. Texas Instruments, another company working on integrated circuits, also benefited from the space race and the Cold War. Jack Kilby invented the first integrated circuit at T, but it was Pat Haggerty, the company president, who understood the potential for selling these chips to the military. Haggerty believed every piece of military electronics could eventually use integrated circuits. He successfully pitched the idea to the Air Force, securing contracts for the Minuteman II missile program. This missile needed a smaller, lighter computer than its predecessor, and integrated circuits were the key. Miller emphasizes that Haggerty's vision of supplying the military was a turning point for T. However, simply inventing the chip wasn't enough. Making them reliably and in large numbers was a huge challenge. J. Lathrop, working at Texas Instruments, came up with a process called photolithography. This used light and special chemicals to print tiny patterns onto silicon, creating the circuits. It was like using a very precise stencil. This process allowed for mass production, but it required solving many problems. The chemicals needed to be incredibly pure, the equipment had to be precise, and the process had to be carefully controlled. Engineers like Morris Chang and Mary Ann Potter spent countless hours experimenting to find the right conditions. Miller highlights that it wasn't just scientific breakthroughs, but also painstaking engineering and problem-solving that made mass production possible. As the technology improved, the price of integrated circuits began to fall. Noyce deliberately lowered prices, even selling chips at a loss sometimes, to encourage more people to use them. He believed a larger civilian market would be more valuable than relying solely on the military. Miller points out that Noyce didn't want the government dictating Fairchild's research. He wanted to focus on creating products for everyday use. By the late 1960s, the computer industry was buying as many chips as the military, and Fairchild was a major supplier. The author explains that the desire to get rich also played a big role in the growth of the semiconductor industry. Fairchild didn't offer its employees stock options, meaning they didn't share in the company's success. This led many talented engineers to leave and start their own companies, hoping to strike it rich. The combination of technological innovation, government funding, and the lure of wealth created a dynamic and competitive environment in Silicon Valley. Miller concludes that the story of the microchip isn't just about science and engineering. It's also about ambition and the pursuit of financial success. Part 2. The Circuitry of the American World. Chris Miller begins by recounting a surprising visit to Stanford University in 1959, just after the Soviet Union launched Sputnik, the first satellite to orbit Earth. A Soviet engineer named Anatoly Trutko arrived to study American technology, including the newly invented integrated circuit. This event highlights the intense competition between the US and the Soviet Union during the Cold War, a race to be the most advanced in science and technology. Despite fears about Soviet progress, the US allowed Trutko and other Soviet scientists to study in America, recognizing that Silicon Valley was quickly becoming the global leader in semiconductors. Even adversaries had to pay attention to what was happening in California. Miller explains that both the US and the Soviet Union understood the importance of semiconductors for manufacturing, computing, and military power. The Soviets, like the Americans, began building their own semiconductor facilities and training scientists. Yuri Osakhin, a talented Soviet engineer, successfully created an integrated circuit in 1962, demonstrating the USSR's growing capabilities. However, the author points out that while the Soviets were making progress, they were still behind the US. American spies were actively trying to acquire Soviet chips to assess their quality, and reports indicated the US was only a few years ahead. The author then introduces a fascinating story of espionage. Joel Barr and Alfred Sarant, two American electrical engineers and committed communists, became spies for the Soviet Union during the Cold War. They provided valuable information about American electronics, even after the Rosenberg spy case led to increased scrutiny. After fleeing to the Soviet Union, Barr and Sarant convinced Soviet leaders to invest in a dedicated city for semiconductor production, envisioning a Soviet Silicon Valley. They successfully persuaded Nikita Khrushchev, the Soviet leader, to fund the project by highlighting the potential of miniaturized technology, like tiny televisions. This led to the creation of Zelenograd, a city outside Moscow designed to be a hub for semiconductor research and production. Miller emphasizes that while Zelenograd aimed to replicate Silicon Valley, it differed significantly in its approach. The Soviet system was centralized and focused on military applications, while Silicon Valley thrived on innovation, competition, and a focus on consumer products. The author notes that the Soviet strategy of simply copying American designs proved ineffective, as the US continued to rapidly advance the technology. Miller then shifts focus to Japan, highlighting its unique role in the semiconductor story. Akio Morita, the founder of Sony, recognized the potential of transistors and traveled to the US to secure a license to produce them. While initially dismissed by American companies as only useful for hearing aids, Morita saw a much larger opportunity in consumer electronics. Japan's government supported the growth of its electronics industry, and Sony successfully produced affordable transistor radios, gaining a foothold in the global market. The author explains that the relationship between the US and Japan was complex. The US initially helped rebuild Japan's economy after World War II, seeing a strong Japan as a valuable ally against communism. While there were concerns about Japanese competition, the US generally allowed Japan to develop its electronics industry, recognizing its strategic importance. Japanese companies like Sony focused on innovation and marketing, while often relying on American technology through licensing agreements. Finally, Miller discusses the role of labor in the semiconductor industry. He introduces Charlie Spork, a production manager who prioritized efficiency and opposed labor unions. Spork recognized the need for cheap labor and began outsourcing assembly work to Asia, starting with Hong Kong and then expanding to countries like Malaysia and Singapore. The author details how companies took advantage of low wages and a non-unionized workforce in these countries, leading to the rise of Asian manufacturing hubs. He notes the irony of the transistor girl's image, a stereotypical depiction of Asian women assembling semiconductors, and the exploitation inherent in the system. Miller concludes by emphasizing that the globalization of semiconductor production was driven by economic factors, but also had significant social and political implications. During the Vietnam War, even as Texas Instruments employees flew between factories and glimpsed battlefields below, the company was already becoming crucial to modern warfare. Initially, T made chips for huge nuclear missiles, but the war in Vietnam demanded different kinds of weapons. The U.S. dropped more bombs during this conflict than in all of World War II in the Pacific, yet many missed their targets. The military realized they needed to be smarter, not just stronger. Early attempts at guided missiles had mixed results, and many simply didn't work well. The problem, as Chris Miller explains, wasn't the idea of guidance, but the technology used. Many early guided weapons relied on vacuum tubes, which were fragile and prone to failure, especially in the hot, humid climate of Southeast Asia. A missile's radar system might break down every few hours. This meant that even with guidance systems, hitting a target was incredibly difficult. It seemed impossible for guided weapons to truly decide the outcome of a war. Weldon Word, an engineer at T, believed microelectronics held the key. He envisioned a future where sensors, satellites, and airplanes worked together to find, track, and destroy targets. This sounded like science fiction at the time, but T already had the building blocks. Word understood that the best weapons weren't necessarily the most complex, but the simplest and most reliable. He wanted to create weapons that were affordable and easy to use, something that could be widely adopted by the U.S. and its allies. The turning point came with the development of the Paveway laser-guided bomb. Instead of trying to build a completely new weapon, Word's team took a standard bomb and added wings and a simple laser guidance system. A sensor divided a laser beam into 4 parts. If the bomb drifted off course, the system would adjust the wings to steer it back on target. This dramatically improved accuracy. In 1972, these bombs were used to finally destroy the Than Hoa Bridge in North Vietnam, a structure that had withstood hundreds of previous attacks. A simple laser and a few transistors had transformed a largely ineffective weapon into a precision tool. However, Miller points out, the arrival of these advanced bombs didn't win the war in Vietnam. It did, however, serve as a testing ground for technologies that would revolutionize warfare. Few people realized at the time that Vietnam was a proving ground for a new era of military power. Meanwhile, Texas Instruments began looking to Asia for cheaper production. Mark Shepard, a T executive, initially had a difficult time in Taiwan, clashing with officials over intellectual property and cultural differences. But Taiwan's economy minister, KT Lee, realized that a partnership with T could bring economic growth and strengthen Taiwan's ties with the U.S. at a time when America's commitment to its allies was uncertain. The situation was complicated by the Cold War. The U.S. feared the spread of communism in Asia, and Taiwan needed reassurance that it wouldn't be abandoned. Miller explains that semiconductors became a key part of this strategy. Taiwan offered low labor costs and a growing pool of skilled engineers. T's investment helped to create jobs and build industry, while also strengthening Taiwan's relationship with the U.S. Other countries, like Singapore and Malaysia, followed suit, becoming hubs for semiconductor assembly. This created a new alliance between American chipmakers, Asian governments, and the workers who assembled the chips. Semiconductors transformed the economies of these countries, providing jobs and driving economic growth. By the 1980s, the electronics industry was a major part of the economies of Singapore, Hong Kong, and Malaysia. These supply chains became a vital link between the U.S. and Asia, even as America's military presence in the region declined. As Chris Miller details, the story then shifts to Intel and the birth of the microprocessor. Bob Noyce and Gordon Moore left Fairchild Semiconductor to found Intel, driven by a desire for more control and a belief in the power of integrated circuits. Intel's first product was a memory chip, but the company soon turned its attention to creating a computer on a chip, the microprocessor. This was sparked by a request from a Japanese calculator company, Busicom. Ted Hoff, an Intel engineer, realized that a single, programmable chip could replace the many custom-designed circuits needed for different calculators. The result was the Intel 4004, the world's first microprocessor. This chip could be used in a wide range of devices, and it marked a turning point in the history of computing. Carver Mead, a Caltech professor, predicted that microprocessors would revolutionize society, putting computing power into everything from telephones to cars. Finally, Miller describes how the Pentagon, under William Perry, recognized the potential of these new technologies. Perry, a former Silicon Valley engineer, understood the power of microelectronics and pushed for investment in guided missiles, satellites, and advanced sensors. Andrew Marshall, a Pentagon strategist, argued that the U.S. needed to offset the Soviet Union's numerical advantage with superior technology. The goal was to create weapons that were so accurate and effective that they would deter the Soviets and change the nature of warfare. The Pentagon's offset strategy relied heavily on the continued advancement of microchips, and the U.S. military became increasingly dependent on Silicon Valley's innovation. Part 3: Leadership Lost. Chris Miller details a period in the 1980s when the United States faced a serious challenge to its dominance in the semiconductor industry from Japan. This wasn't just about making better gadgets, it was about controlling a crucial technology. Semiconductors, or microchips, are the brains of almost all modern electronics, from computers and phones to cars and washing machines. Whoever controls the chip industry has a lot of power. The story begins with Richard Anderson, a key decision-maker at Hewlett-Packard, a major American tech company. Chip salesmen were desperate to convince him their chips were the best, because HP was a huge buyer. But Anderson's job revealed a troubling trend. Japanese chips were becoming better quality than American ones. Miller explains that for decades, the United States had been the leader in chip technology. Silicon Valley was seen as the place where all the innovation happened. But Japanese companies like Toshiba and NEC were catching up, and quickly. Initially, many in Silicon Valley didn't take the Japanese seriously, even joking about them simply copying American ideas. However, Anderson's testing showed a clear difference. Japanese chips had significantly lower failure rates than American chips, meaning they were more reliable. This wasn't just a small difference. The best American chips failed 4.5 times more often than the best Japanese ones. This meant that if you bought an American chip, you were much more likely to have a device break down. The author highlights that this competition wasn't just about chips themselves. It was about a different approach to manufacturing and business. While American companies focused on innovation and inventing new things, Japanese companies excelled at taking existing ideas and making them better, cheaper, and more reliably. Sony, for example, didn't necessarily invent the transistor radio, but they made it a global success. They then used that success to push into other areas, like TVs and, famously, the Walkman. The Walkman, introduced in 1979, was a huge hit, demonstrating Japan's ability to not just copy, but to innovate and create products people really wanted. It contained 5 of Sony's own integrated circuits, showing they were mastering the core technology. Miller points out that the United States actually helped Japan build its semiconductor industry after World War II. American authorities shared knowledge about transistors, and policymakers allowed Japanese companies to sell their products in the U.S. market. The goal was to create a democratic, capitalist Japan, but it ended up creating a powerful economic competitor. This led to concerns in America about whether they had inadvertently given Japan the tools to challenge their economic and technological leadership. The author introduces Charlie Spork, an executive who had seen firsthand the challenges of American manufacturing. He had previously dealt with labor issues at General Electric and now saw the same problems in the chip industry. Spork sent a team to Japan to study their semiconductor factories. What they found was striking. Japanese workers were incredibly dedicated to their companies, often prioritizing their jobs over even their families. This level of commitment, combined with efficient manufacturing processes, gave Japanese companies a significant advantage. Spork made a film about their experience, showing American workers how tough the competition was. Miller then shifts to the personalities involved in this economic battle. Jerry Sanders, the CEO of Advanced Micro Devices, AMD, was a fierce competitor who wasn't afraid of a fight. He understood the stakes were high. Similarly, Charlie Spork saw the competition with Japan as a war, not a military one, but an economic war fought with technology, productivity, and quality. Spork believed Japan was benefiting from unfair advantages, like intellectual property theft, protected markets, and government subsidies. There were documented cases of Japanese companies spying on American firms to steal secrets, like Hitachi's attempt to photograph a Pratt and Whitney facility. The author notes that while spying was illegal, it was also common in Silicon Valley, with companies constantly suing each other and poaching employees. However, the scale and organization of Japanese espionage raised concerns. Miller also explains that Japan's domestic market was largely closed to American chip makers, while Japanese companies had easy access to the U.S. market. Additionally, the Japanese government provided financial support to its chip makers, while American companies faced stricter regulations and higher interest rates. This combination of factors allowed Japanese companies to invest heavily in new facilities and equipment, gaining a significant advantage over their American rivals. Miller concludes by focusing on GCA Corporation, an American company that was once a leader in lithography, the process of creating patterns on silicon wafers. GCA's success was initially driven by its innovative stepper technology, but the company became complacent and lost its edge to Nikon, a Japanese competitor. GCA's problems were largely self-inflicted, with poor management, excessive spending, and a lack of focus on quality and customer service. The author emphasizes that while government subsidies and market access played a role, GCA's downfall was primarily due to its own internal issues. The story of GCA serves as a cautionary tale about the importance of innovation, efficiency, and customer focus in a competitive market. In the 1980s, a surprising comparison began to surface. Semiconductors, or microchips, were being called the crude oil of the 1980s. Chris Miller explains that this wasn't just marketing talk from Jerry Sanders, the CEO of AMD, a chip-making company. It was a serious realization that control over these tiny pieces of silicon meant control over the entire electronics industry, and therefore, a lot of power. Just like countries fought for control of oil, the U.S. began to worry about falling behind in chip production, especially as Japan rose to become a major player. The U.S. had learned a hard lesson about relying on other countries for important resources during the oil crises of the 1970s. When Arab nations cut off oil supplies, the American economy suffered. This led to high prices and a difficult time for many people. Miller details how the U.S. responded by focusing on securing oil supplies, even using its military to protect them. The fear was that if America didn't control its access to oil, it would be vulnerable. Now, with semiconductors becoming equally essential, found in everything from computers and cars to microwaves and even Walkmans, the U.S. started to worry about the same thing happening with chips. Initially, American chip companies hadn't paid much attention to the government. They were too busy making money from the booming computer market. But as Japan's share of the chip market grew, things changed. Leaders from companies like Intel, AMD, and Fairchild, all founded by people who had once worked together, realized they needed help. They met secretly and decided to ask Washington for support. They formed the Semiconductor Industry Association to lobby the government, hoping to get policies that would help American companies compete. The U.S. military quickly understood the importance of semiconductors. Miller points out that the Pentagon, the headquarters of the U.S. military, knew chips were even more important than oil. Since the 1970s, the military had been using chips to make its weapons systems more advanced. Chips allowed for better guidance systems in missiles, improved communication, and more effective command and control. The U.S. was using technology to stay ahead of the Soviet Union in the Cold War, and semiconductors were key to that strategy. However, by the 1980s, Japan was becoming the dominant force in chip production, even controlling the machines needed to make the chips, a technology invented in the U.S. This was a huge problem. The Defense Department, worried about relying on a potential competitor for critical technology, started working with industry leaders like Bob Noyce and Jack Kilby to find a solution. They created a report outlining the risks and emphasizing that the U.S. military's strength depended on having access to the latest chip technology. The report highlighted that a growing percentage of military spending was going towards electronics, and semiconductors were at the heart of it all. The concern was that if the U.S. lost its edge in chip making, it could become dependent on foreign sources, just like it had been with oil. The situation was complicated by the fact that Japan was an ally of the U.S. After World War II, the U.S. had helped rebuild Japan and encouraged it to become a strong economic power. However, Japan chose to invest heavily in its economy rather than its military, allowing it to become a manufacturing powerhouse. Miller explains that this division of labor, the U.S. focusing on defense while Japan focused on economics, no longer seemed fair. Japan's economic success was now challenging America's military and technological leadership. The U.S. government tried several approaches to help the semiconductor industry. They cut taxes to encourage investment, strengthened intellectual property laws to protect American inventions from being copied, and even considered providing direct financial support. However, these measures weren't enough. The Pentagon and industry leaders pushed for more action, and eventually, the U.S. and Japan reached a trade agreement in 1986. This agreement limited Japan's exports of DRAM chips, a type of memory chip, to the U.S. The idea was to raise prices and help American companies, but it mostly benefited Japan. Ultimately, the U.S. created a consortium called Semitech, a partnership between chip makers and the Defense Department, to try and revitalize the American semiconductor industry. Led by Bob Noyce, Semitech aimed to improve manufacturing processes and coordinate research and development. However, even with Noyce's leadership and significant investment, Semitech struggled to succeed. One of its biggest failures was its attempt to save GCA, an American company that made lithography equipment, the machines used to etch circuits onto chips. Despite receiving millions of dollars in support, GCA couldn't compete with Japanese companies like Nikon and Canon and eventually went out of business. Miller concludes that the story of the 1980s semiconductor battle is a cautionary tale. It shows how quickly a country can lose its technological leadership and the challenges of trying to regain it. It also highlights the complex relationship between government, industry, and national security, and the importance of investing in research and development to stay ahead in a rapidly changing world. Part 4, America Resurgent. Chris Miller details how the United States managed to bounce back from a serious challenge to its dominance in the world of computer chips, a challenge initially posed by Japan and later complicated by the rise of South Korea. It's a story filled with unlikely heroes, government intervention, and a bit of luck. In the 1980s, Japan was making huge strides in producing DRAM chips, the kind of memory chips that help computers remember things. American companies were struggling to compete, facing lower prices and higher quality from Japanese manufacturers. This led to fears that the U.S. was losing its edge in a crucial technology. The author highlights Jack Simplot, a potato farmer, as a surprising figure in this turnaround. Simplot, known as Mr. Spud, didn't understand the technical details of chip making, but he understood business. His company, Micron, invested in DRAM chips at a time when most other American firms were giving up. Simplot recognized that when prices were low due to oversupply, it was a good time to buy and build a business. He saw the Japanese competition as creating a commodity market, meaning the chips were becoming standardized and price was the main factor. This was similar to the potato market, where he had already found success. Miller explains that while Silicon Valley companies initially sought government protection through tariffs and trade restrictions, Simplot took a different approach. He focused on cost-cutting and efficiency. Micron found ways to make chips more cheaply than anyone else, even if they weren't the most technologically advanced. They simplified manufacturing processes, tweaked existing equipment, and focused on maximizing output from each silicon wafer. This strategy, combined with lower labor and electricity costs in Idaho, gave them a competitive advantage. The author points out that the U.S. government's role wasn't always direct financial support. DARPA, a defense research agency, played a crucial role by funding university research in chip design. This led to new tools and techniques that made chip design more efficient and accessible. Researchers like Carver Mead and Lynn Conway developed methods to automate chip design, allowing engineers to create complex circuits more quickly and easily. This was a major breakthrough, and it helped the U.S. maintain its lead in chip technology. Miller also details how the U.S. indirectly helped South Korea emerge as a major chip producer. American companies, looking for ways to lower costs and compete with Japan, began outsourcing production to South Korea. This provided Korean firms like Samsung with access to technology and expertise. The U.S. also encouraged competition by not restricting trade with South Korea, believing that a more diverse supply chain would be beneficial. This strategy, while intended to counter Japan, ultimately led to the rise of a new competitor. The author emphasizes that the story isn't just about technology, but also about leadership and a willingness to take risks. Andy Grove, the CEO of Intel, made the difficult decision to abandon the DRAM market and focus on microprocessors, the brains of computers. This was a gamble, but it paid off as the personal computer market exploded. Grove's leadership style was demanding and relentless, but it helped Intel adapt to the changing landscape. Miller concludes that the U.S. resurgence in the chip industry was a result of a combination of factors: entrepreneurial spirit, government investment in research, strategic partnerships, and a willingness to embrace competition. It was a complex story with no easy answers, but it demonstrates the importance of innovation, adaptability, and a long-term vision in maintaining technological leadership. The author sets the stage for further exploration of how these dynamics continue to play out in the context of the growing rivalry between the U.S. and China in the 21st century. Chris Miller details how the late Cold War and the early 1990s revealed the surprising importance of tiny computer chips, called semiconductors, in deciding who would win the battle between the United States and the Soviet Union. It wasn't just about having more tanks or missiles. It was about having the brains to control them, and those brains relied on increasingly complex chips. The story begins with a frustrated KGB spy, Vladimir Vetrov, whose life was far from glamorous. He was stuck in a boring job, and his personal life was a mess. This led him to betray his country, revealing the extent of the Soviet Union's desperate attempts to steal Western technology. The Soviets had a plan called Copy It, led by Minister Shokin, to simply duplicate American chips and technology. They created a special division, Directorate T, with hundreds of spies dedicated to this task. They stole chips, bought them on the black market, and even blackmailed people to get their hands on the latest designs. For example, a team of 60 agents in San Francisco targeted Silicon Valley companies, and one thief, nicknamed One-Eyed Jack, hid stolen chips in his leather jacket. However, simply having a chip wasn't enough. The Soviets struggled to actually make these chips at a large scale and with good quality. Building these chips became harder and harder as they got more complex, and the Soviets lacked the equipment and expertise to keep up. They stole manufacturing machines, but even those broke down and were difficult to repair without original parts. This meant their military systems often had to rely on simpler, less effective technology. The story of Vetrov is important because his betrayal revealed just how much effort the Soviets were putting into stealing technology, and how little success they were having. He started sending secrets to French intelligence, providing thousands of pages of documents about Directorate T. This led to Operation Exodus, a U.S. effort to tighten controls on technology exports. While this slowed down the flow of chips to the Soviet Union, Miller argues it wasn't a complete success. The Soviets always lagged behind, typically half a decade behind the latest American technology. Meanwhile, a Soviet military leader, Marshal Agarkov, realized the growing importance of precision weapons powered by these chips. He warned that the Soviet Union was falling behind, and that quality was becoming more important than quantity. He predicted that advanced technology would turn conventional weapons into weapons of mass destruction. This was a direct response to Bill Perry's offset strategy, which focused on investing in advanced technology to give the U.S. an advantage. The Soviets tried to respond, but their system couldn't keep up. They lacked the skilled engineers, the efficient manufacturing processes, and the consumer market that drove innovation in the West. The Gulf War in 1991 proved Agarkov right. American weapons, guided by advanced chips, easily defeated the Iraqi military, which relied on Soviet-made equipment. The Paveway laser-guided bomb, a technology developed with the help of Texas Instruments, was particularly effective. This war demonstrated the power of precision technology and the importance of semiconductors. It was a clear victory for the United States and a stark warning to the Soviet Union. As the Soviet Union crumbled, its leaders finally realized the extent of their technological disadvantage. Gorbachev visited Silicon Valley seeking access to American technology, admitting that the ideas and technologies of tomorrow are born here. The Cold War was over, and the United States had won, not just because of its military strength, but because of its ability to innovate in the world of microchips. Miller emphasizes that the Soviet Union's failure wasn't just about a lack of resources, but a fundamental flaw in its economic and political system, which stifled innovation and prevented it from keeping pace with the rapid advancements in semiconductor technology. The story serves as a cautionary tale about the importance of technological leadership and the dangers of falling behind. Part 5: Integrated Circuits, Integrated World. In 1985, a powerful Taiwanese official named KT Lee asked Morris Chang to lead Taiwan's effort to build its own chip industry. Lee had been instrumental in getting companies like Texas Instruments to build factories in Taiwan decades earlier, and he understood how important chips were for jobs, technology, and even national security. He essentially gave Chang a blank check, asking how much money he would need to make Taiwan a major player in the semiconductor world. This marked the beginning of a deliberate strategy by Taiwan to become a key part of the global chip supply chain. The 1990s saw the rise of globalization, but the chip industry had always been international. Taiwan had been involved in assembling chips since the 1960s, but it wanted to do more than just put chips together. It wanted to design and make the most advanced chips, capturing more of the profit. While Taiwan was good at assembling, the real money was made by companies that created and manufactured the chips themselves. This is where Morris Chang came in, and his company, Taiwan Semiconductor Manufacturing Company, or TSMC, would become central to this plan. Taiwan wasn't alone in trying to climb the semiconductor ladder. South Korea was investing heavily in memory chips, and Singapore and Malaysia were trying to copy South Korea's success. However, Taiwan faced a growing threat from China. After Mao Zedong died in 1976, China began to open up its economy, attracting manufacturing jobs with its low wages. This threatened Taiwan's assembly business, as China could offer even cheaper labor. Taiwanese officials saw this as economic warfare and realized they needed to focus on advanced technology to stay competitive. Morris Chang was a key figure in this story. He had spent over 2 decades at Texas Instruments, helping to build the semiconductor industry. He had been passed over for the CEO job at T and felt undervalued, so when Taiwan offered him a chance to lead their chip industry with significant funding, he took it. Interestingly, despite the offer being to lead Taiwan's chip industry, Chang's strongest connection to the island was through the T facilities he helped establish. He had lived most of his life in the United States and even held a U.S. security clearance. He felt more Texan than Taiwanese, but he saw the opportunity to build something significant. Chang's idea was radical for the time. He wanted to create a company that would only manufacture chips designed by other companies. Traditionally, chip companies like T, Intel, and Motorola designed and made their own chips. Chang believed there would be a growing demand for chips from companies that didn't have the expertise or resources to manufacture them themselves. He predicted that, as chips became more complex and expensive to make, only companies producing large volumes could stay competitive. His idea was initially rejected by his colleagues at Texas Instruments in 1976, who didn't see a market for this type of service. However, Chang never forgot the concept. He believed it would become more viable as chip design and manufacturing became more separate, a concept championed by researchers Lynn Conway and Carver Mead. When he was offered the position in Taiwan, he saw a chance to put his idea into practice. The Taiwanese government provided substantial funding for TSMC, with 48% of the startup capital coming from the government itself. They also helped secure a deal with Philips, a Dutch semiconductor company, for technology and investment. The government even asked wealthy Taiwanese families to invest, sometimes using strong persuasion from high-ranking officials. From the beginning, TSMC was a project of the Taiwanese state, designed to boost the nation's economy and technological capabilities. TSMC's success was built on attracting talent from the United States. Many of its employees had worked for American chip companies, and its executives were often educated at top U.S. universities. This close relationship with the U.S. chip industry was crucial, as most of TSMC's early customers were American companies. This partnership benefited both Taiwan and Silicon Valley. It gave chip designers a reliable manufacturing partner, and it helped Taiwan climb the semiconductor value chain. However, this success also created a new dynamic in the industry. While it lowered the barriers to entry for chip designers, it also led to consolidation in manufacturing. The economics of chip making meant that the companies producing the most chips had a significant advantage. TSMC's relentless improvement in manufacturing processes allowed it to dominate the industry, becoming the world's leading chip manufacturer. Meanwhile, in 1987, Ren Zhengfei founded Huawei in China. While Chang aimed to build advanced chips and win over Silicon Valley, Zhengfei started by trading telecommunications equipment. China was still far behind in semiconductor technology, but it was beginning to emerge as a global manufacturing hub. The author, Chris Miller, highlights the stark contrast between Taiwan's ambition to create cutting-edge technology and China's initial focus on assembly. China's early attempts at semiconductor production were hampered by its political history. After the Communist Revolution in 1949, the government was suspicious of foreign connections and prioritized self-reliance. This led to a period of isolation and stagnation, particularly during the Cultural Revolution in the 1960s and 70s, when scientists and engineers were persecuted and sent to work in the countryside. While other Asian countries were building their semiconductor industries, China was falling further behind. Even after Mao's death in 1976 and the beginning of economic reforms, China faced significant challenges. It lacked the expertise, infrastructure, and investment needed to compete with established players like the US, Japan, and Taiwan. The government identified electronics as a priority, but its attempts to control the industry often stifled innovation. The story of Richard Chang, who founded SMIC in 2000, illustrates China's struggle to build a domestic semiconductor industry. Chang, a Taiwanese-American engineer, believed he could replicate TSMC's success in China. He secured significant funding from both international investors and the Chinese government and hired hundreds of foreign engineers, particularly from Taiwan, to help build and operate SMIC's factories. While SMIC made progress, it faced challenges in acquiring advanced technology and competing with established foundries. Miller emphasizes that China's efforts to build a semiconductor industry were often hampered by a lack of trust in foreign technology and a desire for complete self-reliance. However, the author also points out that the success of companies like TSMC and SMIC demonstrates the importance of attracting foreign expertise and investment. The battle for control of semiconductor technology was intensifying, with Taiwan, South Korea, and China all vying for dominance. In 1992, John Carruthers at Intel asked for a huge amount of money, $200 million, to work on a new kind of technology for making computer chips. This technology used extreme ultraviolet, EUV light, which is a special type of light that could make chips even smaller and faster. Most people thought it was impossible, but Intel knew that if they didn't find a way to make smaller chips, they would fall behind. Andy Grove, the CEO of Intel, agreed to give Carruthers the money, knowing it was a big risk. This marked the beginning of what Chris Miller calls the lithography wars, a race to find the best way to build the next generation of computer chips. The problem was that making these tiny chips required incredibly precise tools. For years, the chip industry had relied on using light to carve circuits onto silicon. But as chips got smaller, the light waves needed to be even smaller and more focused. This led to a competition between different technologies, like using X-rays or EUV light. It was a time of intense debate among scientists and engineers, each believing their method was the best. Beyond the technical challenges, there were also business and political issues at play. Companies like Canon and Nikon of Japan dominated the market for chip-making tools, but a small Dutch company called ASML was starting to gain ground. ASML had a unique strategy. Instead of trying to build everything themselves, they focused on putting together the best parts from different companies around the world. This allowed them to be more flexible and innovative. They also benefited from being located in the Netherlands, which was seen as a neutral country during trade disputes between the US and Japan. ASML's success was also linked to a surprising partnership with Taiwan's TSMC, a company that became a major chip manufacturer. This partnership started because of a previous connection between Philips, the company that created ASML, and TSMC. As the chip industry became more global, politics started to play a bigger role. After the Cold War, many people in the US believed that trade and cooperation would lead to peace and prosperity. They thought that countries would focus on making money rather than fighting each other. However, Andy Grove, the former Intel CEO, worried that the US was becoming too reliant on other countries for important technologies. He argued that the US needed to invest in its own manufacturing capabilities to avoid losing its competitive edge. Intel tried to develop EUV technology with the help of US national labs, but they realized that no American company could actually build the machines needed to mass-produce chips using EUV. They considered working with Japanese companies, but ultimately decided that ASML was the only viable option. This raised concerns in Washington about giving a foreign company access to such important technology. Despite these concerns, the US government allowed ASML to proceed, believing that it was the best way to ensure that EUV technology would become available. The story of ASML and EUV shows how complex the chip industry had become. It wasn't just about technology anymore. It was also about business, politics, and international relations. Chris Miller points out that the US government's decision to rely on ASML was based on a belief that globalization would promote peace and cooperation. However, this belief was challenged by the rise of China and its growing ambitions in the technology sector. Meanwhile, Intel was incredibly successful with its x86 computer chips, dominating the market for PCs and servers. But the company missed a major opportunity when it turned down a chance to build chips for Apple's iPhone. Intel's leaders were focused on maintaining high profit margins and didn't see the potential of the mobile market. This decision allowed companies like ARM, a British chip designer, and Samsung, a South Korean manufacturer, to become major players in the mobile industry. ARM had a different business model than Intel. Instead of designing and manufacturing its own chips, ARM licensed its chip designs to other companies. This allowed them to be more flexible and adapt to different markets. The success of ARM and the iPhone showed that the chip industry was changing, and Intel was falling behind. Chris Miller explains that Intel's focus on profits and its reluctance to embrace new technologies led to its downfall in the mobile market. As the 2000s came to a close, Andy Grove warned that the U.S. was losing its edge in manufacturing. He argued that the U.S. needed to invest in its own industries to avoid becoming dependent on other countries. However, his warnings were largely ignored. Many people in Washington believed that the U.S. could run faster than its rivals and maintain its leadership position. But as Chris Miller reveals, this belief was based on a flawed understanding of the chip industry and the changing global landscape. The U.S. was losing ground in key areas, and the consequences would become clear in the years to come. Part 6, Offshoring Innovation. Chris Miller details how owning a semiconductor factory, or fab, was once seen as a sign of strength in the chip industry, famously declared by AMD founder Jerry Sanders as something real men have. Sanders, a master salesman, understood the importance of controlling the manufacturing process, especially during times of competition with Japan and Intel. However, even he recognized the increasing costs associated with building and maintaining these fabs as technology advanced. This is where Morris Chang and TSMC, Taiwan's semiconductor manufacturing company, came into play, pioneering a different approach, becoming a dedicated chip foundry manufacturing chips designed by other companies. The author explains how the semiconductor industry naturally divided into three main areas: logic chips, processors for computers and phones, memory chips, DRAM and NAND for storage, and a more diverse category of analog chips used in sensors and other applications. While logic and memory chips demanded constant shrinking of transistors to stay competitive, analog chips didn't face the same pressure, making their manufacturing less expensive. This difference explains why analog chip production remained largely in the United States, Europe, and Japan, while logic and memory shifted towards Asia. Miller points out that the economics of these different chip types shaped the global landscape of semiconductor manufacturing. The story highlights how memory chip production became heavily concentrated in East Asia, particularly South Korea and Taiwan. Building advanced memory fabs requires enormous investment, around $20 billion, leading to consolidation and a few dominant players like Samsung, SK Hynix, and Micron. While Micron is an American company, much of its manufacturing takes place in Asia, driven by government subsidies and the benefits of scale. This illustrates a key point. Even American companies found it advantageous to produce in Asia. Miller emphasizes the shift in the logic chip market, where many American companies, like Motorola and National Semiconductor, either failed or outsourced their manufacturing to foundries like TSMC. This fabless model, designing chips without owning the factories, allowed companies to focus on innovation and reduce costs. NVIDIA, founded in Adenis, is a prime example of a fabless success story, designing powerful graphics processing units, GPUs, and investing heavily in software to expand their market beyond gaming into areas like artificial intelligence. Qualcomm, another fabless company, revolutionized mobile communications by developing efficient chips for cell phones. The author notes that this move towards outsourcing wasn't simply about cost. It was about specialization. Companies like NVIDIA and Qualcomm excelled at chip design and software development, while TSMC focused on perfecting the art of manufacturing. This division of labor proved incredibly effective, driving innovation and lowering costs. Miller explains that Jerry Sanders's insistence on owning fabs was becoming outdated as the industry evolved. Chris Miller details how Morris Chang's vision for TSMC, creating a grand alliance of companies focused on collaboration and standardization, was crucial to its success. By becoming a neutral manufacturer, TSMC attracted a wide range of customers and fostered innovation across the entire semiconductor ecosystem. Chang's willingness to invest during the 2008 financial crisis, while others cut back, solidified TSMC's position as the dominant foundry. Finally, the author introduces Apple as a major player in chip design, demonstrating how the company's focus on integrating hardware and software led it to develop its own processors. Like NVIDIA and Qualcomm, Apple relies on TSMC for manufacturing, highlighting the central role of Taiwanese foundries in the modern semiconductor industry. Miller concludes by pointing out the irony that while iPhones are designed in California and assembled in China, their most critical components are actually made in Taiwan, revealing a complex and geographically concentrated supply chain. Chris Miller details how the story of extreme ultraviolet, EUV, lithography isn't just about making faster computers, but about a global competition for power between the United States and China. The development of EUV, a super-advanced technology for building microchips, became a high-stakes game where countries raced to control the future of technology. It began with a Dutch company, ASML, trying for decades to perfect EUV, needing parts and expertise from all over the world. This illustrates how modern technology isn't made in one place, but relies on a complex web of international cooperation. The author explains that companies like Intel, Samsung, and TSMC invested heavily in ASML because they knew EUV was essential for making smaller, more powerful chips. Intel, in particular, poured billions into the project, recognizing its importance. This wasn't just about business, it was about maintaining a technological edge. The core idea behind EUV, like earlier lithography techniques, involves using light to create patterns on silicon wafers, but EUV used a much shorter wavelength of light, allowing for even tinier features. However, achieving this was incredibly difficult, requiring innovations in lasers, mirrors, and materials science. Miller highlights the incredible complexity of building an EUV machine. For example, creating the light source involved blasting tiny droplets of tin with powerful lasers, a process repeated 50,000 times per second. This required breakthroughs in laser technology from companies like Cymer and Trumpf, demonstrating how specialized expertise was crucial. The mirrors needed to collect and focus the EUV light were so precise they were the smoothest objects ever made, a feat accomplished by Zeiss. ASML's success wasn't just about its own engineering, but its ability to manage a vast network of suppliers, ensuring everything worked together seamlessly. The narrative then shifts to the story of GlobalFoundries, a US-based chip maker that ultimately decided to give up on trying to compete at the leading edge of chip manufacturing. The author explains that GlobalFoundries realized the cost of developing and maintaining the most advanced technology, like EUV, was simply too high. This decision left only 3 companies, TSMC, Samsung, and Intel, capable of making the most cutting-edge chips. This illustrates a key point. Only the biggest players can afford to stay at the forefront of semiconductor technology. Miller then focuses on Intel, once the undisputed leader in the chip industry. Despite its early investment in EUV and its strong position, Intel stumbled. The author points out that Intel's focus on both chip design and manufacturing may have spread its resources too thin. While TSMC focused solely on manufacturing, constantly improving its processes, Intel had to divide its attention. Furthermore, Intel missed the shift towards specialized chips for artificial intelligence, a market dominated by NVIDIA and increasingly by the large cloud computing companies designing their own chips. The author emphasizes that Intel's delays in adopting EUV were a major factor in its decline. While TSMC and Samsung were using EUV to push the boundaries of chip technology, Intel struggled to get its EUV tools working effectively. This allowed its competitors to gain a significant advantage. The situation highlights a critical issue. The US is now reliant on Taiwan and South Korea for the most advanced chips, a situation that raises national security concerns given the geopolitical tensions with China. The author concludes that the future of American chip manufacturing is uncertain, and Intel's success is crucial for maintaining US technological leadership. Part 7, China's Challenge. Chris Miller details how, despite appearing to embrace globalization, China's leader Xi Jinping was deeply worried about the country's reliance on foreign technology, especially semiconductors, the tiny brains powering everything from smartphones to missiles. Xi believed a strong nation needed to control its own technology, and China was heavily dependent on the United States and its allies for these crucial chips. While China had become very good at using technology, it couldn't make the most important parts. It was like being able to drive a fancy car, but needing to buy the engine from someone else. The author explains that China had successfully built up its own tech companies, like Baidu and Tencent, to compete with Google and Facebook, but these companies still relied on chips made elsewhere. Even the sophisticated surveillance systems China used to track its citizens depended on American-made chips. This was a major security risk for Xi, who feared that the US could cut off the supply of these chips, crippling China's economy and military. Miller points out that China's internet, though heavily controlled, was built on a foundation of foreign hardware. Xi wanted to change that, aiming for a world where China wasn't dependent on others for its most important technologies. Miller describes how China's leaders realized that simply having a large tech market wasn't enough. They needed to own the core technologies, the things the rest of the world couldn't live without. He uses the example of the iPhone. China assembled millions of them, but Apple and the chip makers made most of the profit. Xi wanted China to be in control of the entire process, from design to manufacturing. This meant investing heavily in building its own semiconductor industry. The author notes that, unlike oil, which can be found in many places, the technology to make advanced chips was concentrated in a few countries, mostly rivals of China. The author explains that China's approach involved learning from the successes of other countries like Japan, Taiwan, and South Korea. These nations had all invested heavily in their semiconductor industries, attracted talented engineers from abroad, and formed partnerships with foreign companies to gain access to technology. Miller highlights that China's strategy wasn't just about economics. It was also about national security and becoming a global power. He emphasizes that Xi Jinping viewed this as a battle to be won, using strong language like assault the fortifications to rally his country. Miller details how, in 2017, Xi Jinping presented China as a champion of globalization at the World Economic Forum in Davos, Switzerland. However, behind the scenes, he was urging Chinese tech companies to focus on developing core technologies, particularly semiconductors. This contrasted sharply with the protectionist rhetoric of the incoming US President Donald Trump. The author points out the irony that both leaders, despite their different approaches, were focused on strengthening their own country's technological capabilities. The author explains that China's efforts to build a domestic chip industry faced many challenges. State-owned companies were often inefficient and plagued by corruption. It was difficult to attract top talent and compete with established players like TSMC and Samsung. However, China had a significant advantage: vast financial resources and a government willing to invest heavily in the sector. Miller describes the creation of the Big Fund, a massive investment fund designed to support China's semiconductor industry. Miller illustrates how American companies, like IBM, Qualcomm, and AMD, found themselves in a difficult position. They wanted access to the huge Chinese market, but China often demanded technology transfer as a condition of entry. The author details how IBM offered to share its chip technology with Chinese partners, while AMD sold stakes in its facilities to Chinese investors. These deals raised concerns in the U.S. government, which worried that they were helping China build its own chip industry at the expense of American competitiveness. The author describes the actions of Zhao Weiguo, a Chinese businessman who rose to prominence by investing in the semiconductor industry. Zhao aggressively pursued acquisitions of foreign chip companies, including attempts to buy Micron in the U.S. and TSMC and MediaTek in Taiwan. These efforts were often met with resistance from governments and companies concerned about national security and intellectual property theft. Miller emphasizes that Zhao's actions were part of a broader strategy by China to gain control of the global semiconductor supply chain. Miller concludes by highlighting the high stakes involved in this technological competition. Semiconductors are the foundation of the modern economy, and control over this technology is essential for economic and military power. The author suggests that China's efforts to build a domestic chip industry could reshape the global economy and potentially lead to a new era of technological competition and conflict. He notes that the situation is complex, with both economic and security implications, and that the outcome is far from certain. Chris Miller details the rising importance of Huawei, a Chinese technology company, and how its story is deeply connected to the competition between the United States and China for control of the world's most important technology, semiconductors, also known as microchips. Huawei started as a small company importing telecom equipment, the stuff that makes phone calls work, and grew into a global giant providing everything from cell tower technology to smartphones and cloud computing. It became so widespread that, in many countries, you can't use a phone without using some part made by Huawei, much like how you can't use a computer without Microsoft. However, unlike American tech companies, Huawei has faced constant scrutiny from the U.S. government, which worries about potential security risks. Miller explains that Huawei's success isn't simply because of help from the Chinese government, though that played a role. Instead, Huawei followed a similar path to Samsung, the South Korean tech company. Both companies focused on building strong relationships with their governments to get support, learning from Western and Japanese technology, and then making it cheaper, and expanding globally to compete with the best. Huawei did this exceptionally well, grabbing market share from established companies like Nokia and Ericsson. Unlike many other Chinese tech companies that focus on the huge Chinese market, Huawei aimed to compete worldwide. The author points out that Huawei's rise coincided with a shift in how we think about technology and warfare. Modern warfare isn't just about tanks and planes, it's about having the most advanced computing power. This is where semiconductors come in. Miller explains that each new generation of mobile networks, 1G, 2G, 3G, 4G, and now 5G, has required more powerful chips to send more data faster. 5G isn't just about faster phones. It's about connecting everything cars, coffee makers, medical devices to the internet, creating a massive network of data. This requires even more computing power and, crucially, advanced semiconductors. Miller details how Huawei began designing its own chips, even though it still relied on companies like TSMC in Taiwan to actually make them. This was a huge step, as it meant China was moving closer to being self-sufficient in a critical technology. This alarmed the U.S. because it threatened America's dominance in chip design. The author illustrates this by explaining how Tesla, the electric car company, is also becoming a tech company by designing its own chips to improve its car's performance. This shows how important chips are becoming in all industries, not just technology. The author then shifts focus to the military implications. Miller argues that the future of warfare will be decided by whoever has the most advanced computing power. China is investing heavily in military intelligentization, using artificial intelligence to improve its weapons systems. This includes things like autonomous drones, better radar, and more accurate missiles. The U.S. military recognizes this threat and is trying to develop its own offset, a technological advantage that can counter China's growing military strength. Miller explains that the U.S. military is focusing on things like networking thousands of devices together and using artificial intelligence to make faster, better decisions. However, the U.S. is facing a challenge. It's becoming increasingly reliant on foreign companies, particularly in Taiwan, for the actual manufacturing of these crucial chips. The author highlights that the U.S. government used to be a major buyer of chips, but now it's a small percentage of the market, giving it less influence over the industry. Miller concludes by emphasizing the high stakes of this competition. China is actively trying to become self-sufficient in chip technology, while the U.S. is trying to maintain its lead. The future of both the global economy and military power may depend on who wins this battle for control of semiconductors. Taiwan, where most advanced chips are made, is at the center of this struggle, making it a potential flashpoint for conflict. The author suggests that the U.S. is betting its military future on a technology where its dominance is slipping, making the situation even more precarious. Part 8: The Chip Choke. Chris Miller details a growing worry for American leaders starting around 2015. China was making a big push to become a leader in making computer chips, also called semiconductors. These tiny chips are essential for almost everything: modern phones, cars, computers, and even weapons. Intel's CEO, Brian K. Arzanish, realized this and tried to convince the U.S. government to do something about China's huge investments in its chip industry. The problem was, American companies relied on China as a major market, so they were hesitant to speak out too strongly. It was a tricky situation. The Obama administration initially didn't fully grasp the importance of this issue. Many officials didn't understand what semiconductors even were. They were used to dealing with complaints from industries like steel, but high-tech was supposed to be America's strong suit. However, as they learned more, they became concerned. China was offering billions of dollars in subsidies to its chipmakers, which could potentially put American companies out of business, just like it had done with solar panel manufacturers. One official worried about a $250 billion fund China had created, fearing it would overwhelm the U.S. industry. Despite recognizing the problem, the U.S. government was slow to act. For decades, America had believed in globalization and running faster, meaning staying ahead through constant innovation. This idea was deeply ingrained in both the industry and Washington. But Miller explains that this approach wasn't enough. China wasn't just trying to catch up, it was actively trying to replace American companies in the supply chain. The author points out that the idea of globalization was often oversimplified, and in reality, chip making was becoming concentrated in a few key places, particularly Taiwan. Towards the end of Obama's presidency, the government started to take action. Commerce Secretary Penny Pritzker publicly condemned China's unfair trade practices and its attempts to acquire American technology. However, there wasn't much time left to make significant changes. A report commissioned by the White House actually recommended continuing the run faster strategy, which Miller argues missed the point. Simply innovating wasn't enough when China was receiving massive government support. The Trump administration brought a different approach. While Trump himself wasn't particularly interested in the details of technology, his advisors, like Matt Pottinger, understood the strategic importance of semiconductors. They believed that controlling chip technology was essential for competing in the 21st century. They moved away from the idea of running faster and adopted a more confrontational stance towards China. This shift worried many in the chip industry, who feared retaliation from China. The author illustrates this tension with the case of ZTE, a Chinese telecom company. The U.S. initially restricted American companies from selling to ZTE after it violated sanctions, but Trump later intervened to save the company as part of a trade deal with China. This decision frustrated those within the administration who believed a tougher line was needed. Miller highlights how the national security bureaucracy saw China's tech industry with more skepticism, worrying about potential espionage and the use of technology for military purposes. A key example of this new approach was the case of Fujian Jinhua, a Chinese company attempting to enter the DRAM chip market. Jinhua engaged in industrial espionage, stealing secrets from Micron, an American memory chip maker. Miller details how UMC, a Taiwanese company, was used as a middleman to acquire this technology. When Micron sued, a Chinese court sided with Jinhua, effectively banning Micron from the Chinese market. The Trump administration responded by cutting off Jinhua's access to U.S. equipment, effectively shutting down the company. This demonstrated the U.S. ability to weaponize its control over key parts of the chip-making supply chain. Finally, Miller describes the U.S. government's actions against Huawei, another Chinese tech giant. The U.S. restricted Huawei's access to American technology, preventing it from designing and manufacturing chips. This was a significant blow to Huawei, forcing it to scale back its operations. The author emphasizes that the U.S. wasn't just concerned about spying. It was about preventing China from becoming a dominant force in a critical technology. While China hasn't retaliated in a major way, Miller argues that the U.S. has gained a significant advantage by controlling key choke points in the semiconductor industry. The author concludes that the U.S. has discovered a new form of economic warfare, using its technological dominance to limit China's ambitions. Chris Miller details a fascinating and increasingly important competition between the United States and China for control of the technology behind semiconductors, also known as microchips. These tiny components are essential for almost everything modern life relies on, from smartphones and cars to medical equipment and national defense systems. The story begins in Wuhan, China, in early 2020, as the COVID-19 pandemic emerged. Even during the strict lockdown of the city, one factory was allowed to continue operating: Yangtze Memory Technologies Corporation, YMTC, a key player in China's ambition to become a leader in chip manufacturing. This demonstrates how seriously the Chinese government views building a strong domestic semiconductor industry, even prioritizing it over public health measures. For a long time, only a handful of companies worldwide could make advanced chips. None were based in China. Miller explains that China sees achieving this capability as vital for its future, much like the United States felt after the Soviet Union launched Sputnik in 1957, sparking a space race and a surge in American science and technology funding. The U.S. has recently taken actions, like banning sales of chips to companies like Huawei, that have actually spurred China to invest even more heavily in its own chip industry. This is because, as analyst Dan Wang points out, the restrictions have created a Sputnik moment for China, forcing them to accelerate their efforts. The debate now centers on whether the U.S. should continue to try and limit China's progress, potentially causing a stronger reaction, or focus on strengthening its own chip industry. Miller highlights the challenges China faces. Building a successful semiconductor industry isn't easy. It requires massive investment, advanced technology, and a skilled workforce. He points to the case of Wuhan Hongxin, HSMC, a company that fraudulently obtained funding by falsely claiming connections to top officials and exaggerating its capabilities. This illustrates the risk of simply throwing money at the problem without proper oversight. Another example is Tsinghua Unigroup, a fund that invested in chip companies globally but eventually ran out of money. These failures show that China's path to semiconductor independence is fraught with difficulties. The author emphasizes that complete independence in chip making is unrealistic for any country, even the United States, due to the complex global supply chain. For China, it's even harder because it lacks expertise in many areas, from designing the chips to making the specialized machines needed to produce them. Miller uses the example of ASML's EUV machines, which are crucial for making the most advanced chips. These machines are incredibly complex, requiring hundreds of thousands of precisely assembled parts. Even if China could obtain the designs, replicating them would be extremely difficult and expensive, requiring decades of experience and expertise. However, Miller doesn't paint a completely bleak picture for China. He notes that China is focusing on areas where it might have a better chance of success, such as older chip technology used in cars and other consumer devices. They are also investing in new materials like silicon carbide and gallium nitride, which are important for electric vehicles. Furthermore, China is embracing RISC-V, an open-source chip architecture that could reduce its reliance on US and British technology. The author predicts that China's share of chip fabrication will increase significantly by 2030, even if it still lags behind technologically. The following chapter shifts focus to the global chip shortage of 2021, triggered by the pandemic. Miller argues that this wasn't primarily a supply chain problem, but rather a result of fluctuating demand and poor planning by some industries, particularly the automotive sector. While the Biden administration framed it as a supply chain issue, the reality was that chip makers had already shifted production to meet the increased demand for PCs and data centers when car companies initially cut their orders. The shortage highlighted the importance of semiconductors and the vulnerability of industries that rely on them. Miller points out that the US and its allies control many key parts of the chip supply chain, including design software and manufacturing equipment. He notes that countries like South Korea, Taiwan, and Japan are also major players and have their own interests. The US is trying to encourage companies like TSMC and Samsung to build more factories in the US, but these companies are also investing in their home countries and elsewhere. The author suggests that the US needs a leader like Andy Grove, who transformed Intel into a powerhouse, to guide its chip strategy. The final section of the chapter focuses on the geopolitical risks surrounding Taiwan, where TSMC is based. Miller explains that Taiwan's chip industry is a critical asset, and a conflict in the Taiwan Strait could have devastating consequences for the global economy. He details how China has been increasing its military capabilities and conducting exercises near Taiwan, raising concerns about a potential invasion. He also notes that even without a full-scale invasion, China could use economic pressure or a blockade to try and gain control of TSMC. The author draws parallels to the Russia-Ukraine war, highlighting how Russia's reliance on foreign semiconductors has weakened its military capabilities. Ultimately, Miller argues that the situation in Taiwan is incredibly precarious, and that the world's dependence on Taiwanese chips creates a significant vulnerability. And that brings us to the end of our summary of this book. I hope you found it insightful and valuable. If you enjoyed this video, hit like and subscribe for more. Your support helps us bring you more great content. Thanks for watching.